Okay, so we were looking at uh, embeddings and semantic search in the last lecture. Just to recap, we defined something called cosine similarity, which is the how similar are two embeddings in this equation. For example, x and y represent the embedding in some dimension, like 128, 256, 1000 dimensions, whatever. The dimension is something that's picked ahead of time. And then the cosine similarity measures how similar is embedding x to embedding y. And this quantity is between -1 and 1. And we saw an example where we asked this question if we should recommend the movie Avatar to Michael based on their 4-dimensional embedding that's given here as an example. And I think the answer was the answer yes or no? I think it was no. So because I think the cosine similarity was negative in this case. Okay. Um, so we also said that you can embed objects, two different kinds of objects, like you can embed users and also objects in the same space, and then ask questions that connect the two different kinds of objects. So you can also so you can do different kinds of comparisons. You can say, does this person like this particular object, or does this person like this particular movie? Or you can also compare, sentences to words. So there's different ways you can use embedding. So if I want to say, I love to drive cars and paint flowers too, which object is it close to? You'd say, okay, I see cars here, I see flowers here, so it should be close to cars and flowers, and maybe even road, but probably not food. So if I had an embedding for this sentence, that's kind of like right in the middle here, this gray line, that's close to cars and flowers. So that checks the box on this sentence embedding being close to the word embedding for cars and word embedding for flowers. So if we pick an embedding, whatever embedding it is, OpenAI embedding or Glove embeddings, regardless of what you're comparing, everything will have the same dimension, right? If it's a single word, it's going to have the same dimension. If it's a complete sentence or a paragraph or even a whole document, it's still going to have the same dimension. And we said that if you only know the word embeddings and you wanted to get the sentence embedding, one way to do that is averaging. You just take all the words here, get their embeddings, sum it up and divide by the number of words. That's a simple average embedding. Then we also spoke about TF-IDF, term frequency, inverse document frequency based embeddings as well that actually pick on important words. For example, in this sentence, you really don't need to embed I and to and to, because they don't really contribute to the semantics of the sentence. So to understand the sentence, I can actually exclude prepositions and other filler words and just focus on the ones that are important. So if you did TF-IDF, it'd do exactly that. Say, okay, I and to shows up so frequently in so many documents, the inverse document frequency is so high that I'm actually not going to put so much weight on I or to or and, because it almost shows up in every other document. So the inverse document frequency is going to be high. So the weighting is actually low because it's TF-IDF. So you're going to actually focus more on things like love, drive, paint, and flowers in this sentence. So that's a heuristic for sentence embedding. So we can also, so simple average embedding, TF-IDF based embedding, but the more like popular one these days, and the thing that works more, that works better in practice, is actually embeddings that come out of a transformer, like a BERT model, or like even OpenAI has embeddings because they are also transformers. So the way it works when we get to transformers, we'll see that is you take the last token. You'll also see this in assignment too. You take the last token or average of all the tokens of the last layer and use that as an embedding. So instead of looking at one word at a time and averaging it, because then you're not actually capturing correlation between words, you're just averaging them out. The BERT-based embeddings or OpenAI-based embeddings actually look at the whole context, the whole sentence, and then embed it as a whole. Like, um, so that's kind of that could be very different from just an average embedding. Here's an example. If I asked you this question, let's take two words, chocolate and milk. Okay, so chocolate has an embedding, milk has an embedding. If I look at chocolate milk and milk chocolate, are they the same? Are they referring to the same thing? No, right? So one is actually milk and one is actually chocolate, but it is milk chocolate or chocolate milk. So they're different quantities. If I average the embeddings of chocolate and milk to get the sentence embedding for milk chocolate or chocolate milk, would I get the exact same embedding? Right? So averaging has its limitations because it would actually embed milk chocolate and chocolate milk in this exact same vector. You get the exact same vector. So what is the key here? What is the key idea here? The key idea is to capture the order or the sequence in which the words appear. If chocolate appeared before milk, it's actually referring to a milk and not chocolate. And if milk appeared before chocolate, and you're referring to chocolate. So the order of words coming in should matter for an embedding. So that's why BERT-based embeddings or OpenAI embeddings are more nuanced and can capture these differences in semantics because they respect order. They actually look at the order in which the words come in. Okay, so we'll look at more on this when we get to BERT. But yeah, so in the demo today, we'll look at a simple average embedding. We'll also look at a more nuanced embedding and see how the results vary when we switch from one to the other. Okay, any questions on this so far? Okay. And you guys are able to see the screen, right? Okay, cool. All right. So yeah, like we said, for more nuanced embedding, we go through a deep learning model like a BERT model or a OpenAI model or a Llama model. Every single transformer model can give you embeddings. You look at the last but one hidden layer of activations and then use that as embeddings. So I think in mini project 1, we'll also look at sentence BERT as another source of embeddings. Yeah, let's look at, so we'll look at this question of, given a sentence, what's the closest category that you can categorize that sentence into? So we'll look at this particular question in the demo and see if we can, how the embeddings predict categories. And the way we're going to actually narrow down the category is we compute cosine similarity for every single category of a particular query. Like this is a query, the sentence here is a query. And then let's say road, cars, flowers, food, and maybe mountain are the categories. So you want to categorize this sentence into one of the 4 or one of the 5. So you're going to compute the cosine similarity between this sentence and each of the individual category words here, and then sort it and pick the one that has the highest cosine similarity and output that as the result, right? So that's kind of a basic semantic search is, effectively what's happening, even if you, let's say you can extrapolate it anywhere, you can extrapolate it to RAG, retrieval augmented generation. Like if you look at, you go to Google and then you type something and then Gemini outputs a result and it's referencing a certain set of documents, it's actually narrowing down those documents from the billions of documents it has access to. And that's done through a retrieval step, and that's a embedding based retrieval. So you actually use semantic search to filter the documents and then apply, so that's the retrieval part of RAG. And then you can, if you can fit it in context, great, and then Gemini would do something like that and then give you the answer and also reference the document. Say, hey, this is a document I used to actually reference my answer. But the retrieval for that happened through semantic search like we are just discussing right now. So you can replace the sentence with a word, with a paragraph, with a document, with a page. I mean, this can, you can replace it in any way. But the bigger the search query, the more or the bigger the documents, the more nuanced the retrieval becomes, and then so you have to pay more attention to make sure that the retrieval is good. So that's a separate topic. We'll not look into it right now. So using this as like a context, let's go into the demo, and let's look at how it's set up here. So I'm going to switch screens. Let me go to what's going on. Okay. Let me see if I can share my screen here. Okay, I don't know where that's being shared. Okay. Can you guys see my screen? Here, code editor. Yeah. So what I created here is I have two files which I'm going to use for the demo. So the first one is just a class for LLM, right? And specifically for OpenAI, but you can, it's always good to have a class to set up an LLM or load an LLM. It can be OpenAI GPT based LLM, or it can be Llama 3 or whatever is your thing. Have a class around it and then use the class to call the individual methods. That's always a good thing. So here I have an OpenAI key and I have stored it in a file. And then I load that key and then I set up the client based on that key, right? So I import OpenAI from OpenAI and then I set up the, using the key, I set up the client. So this is, so this is a method to just load the key from the file. And then there are two more methods here. One is to get a chat. So there is like, you see this client.chat.completions. The chat is actually the one that's more like, it has gone through reinforcement learning. It's instruction fine-tuned, and it's the one that looks very polished. So that's why there's a chat version. And there's also raw versions that you can have access to with most of the LLMs and that are less polished, that has less of a fine-tuning. So we are using a chat because we want, we're looking for a more nuanced response. But anyway, this is something we're not actually going to use for the demo, but I'm just putting it here. And you see the way these things actually take an input for the chat completion. You encapsulate your prompt into this dictionary structure where you say there's a role, like the role is either user or it's a system prompt or it's a assistant. So it's a response from the model. So typically we usually use a role user, and then the content is the prompt that you're passing in, and then you go through this logic. We say, okay, client.chat.completions.create, what is a model? So by default, this one is looking at GPT-4o mini, but obviously you can change the model, and then the messages are encapsulated as a list. So here we only have a user and the prompt, but you can also have a system role as system. So that's a system prompt. So you can pass in a system prompt and also a user prompt. And so here I'm only passing in the user prompt. You can also add a system prompt here. And then you get the response, and then there is some parsing of that response to actually get the text. So let's actually test this part, and then we'll get to the embeddings part as well. So let's look at the evaluation of this code here. So I set up the client by just calling this class. It does stuff in here. So it's already set up the client here, right? So this is a class instance, and then I am specifying the model to be GPT-4o mini, and I just prompted it what is the height of Mount Everest just to test it. So let's just make sure that works. So I'm going to say Python 3 LLM API, and it should return. Yeah, so Mount Everest has an official height of 8848 meters above sea level. So yeah, so this makes sense. The setup is right. So now let's look at the next one, which is the OpenAI embedding. So any LLM that you pick comes with embeddings, but the model is actually different because it's focused on the embedding. So we don't have GPT-4o or GPT-5 here because this is a different setup for so it's referenced in a different way. So here for OpenAI, you have text embedding 3 small or text embedding 3 large are typically the embeddings that are used. So let's say I set up text embedding 3 small, and then I want to look at the length of the embedding, and I'll do the same for text embedding 3 large. So let's do that. Yeah, so the small one is of dimension 1536, and the large one is double that size, so 3072. So these are actually, there's quite a bit of information in even embedding a single word. It's going to be 1536 dimensions, and anything. I mean, you can embed a sentence, it's going to be 1536 dimensions, or a paragraph or a whole document, it's going to be the same, 1536 dimensions for the small, and then 3072 for the large. So when you do cosine similarity, we are actually looking at this dimension. In class, we're looking at 4 dimensions, but with OpenAI embeddings, we're looking at 1536 at the minimum. Okay. All right, so that's the setup for LLM with OpenAI. And let's go to the embeddings demo file. So here I have a few libraries that I've loaded. So one is NumPy. NumPy is very suitable for mathematical operations, taking dot products of matrices and vectors, or anything that is matrix algebra. I mean, I'm sure most of us have used NumPy. Otherwise, you'll get familiar with it. It's super helpful. And then NumPy also has a linear algebra package it's super efficient, super fast. So that's also something that you can use if needed. For example, to compute cosine similarity, we actually use some of the NumPy libraries here and NumPy operations to set up the cosine similarity. Okay, pickle, I think this is just to load, there's a format to load one of the embeddings. So we're also looking at glove embeddings, which is like the simple word-based embeddings, and then we average those. So that's glove, that's like the baseline. We're also using LLM embedding, so that's why now that we've created this LLM class, so I'm going to import that here, the one that we just looked at. So from LLM API, import LLM. So that's one. The new one here is like this Streamlit, import Streamlit as ST. So Streamlit is like a very easy way to come up with a web-based demo. It's an easy framework to do it. You don't have to worry too much about HTML, CSS, and all of that stuff. You don't have to worry about any front-end coding. You just have to specify how you want to input the data and how you want to display it through higher level abstractions. And then Streamlit takes care of rendering it. So you don't have to worry about rendering. That's the nice thing about Streamlit. It's very good for prototyping and easy demos. So this is something you might be using in Mini Project 1 as well. Okay, so those are the libraries. So we define cosine similarity here. As we know, cosine similarity is the dot product of x and y divided by the norm of x and y. So that's what this line is looking at. But to do this dot product, we need to convert x into a NumPy array format. So that's what this does. Make sure that your format is in NumPy array. Because if you have a list of floats, for example, you get an embedding, it's going to be a list of floats. It might not be in a NumPy format. So you first convert it into NumPy, and then you can do this. So that's cosine similarity. So this one is loading the glove embeddings. So I have a path for that. And then it's going to be a dictionary where for every single word, there's going to be a certain dimensional embedding. So with glove embeddings, which is like, the embeddings are pre-computed. There's no extra computation to get the embedding. You already know the embedding once you load the dictionary, but it's only for a single word. It's not for a sentence. But with OpenAI embeddings, the embeddings are computed on the fly. So you don't know what the embedding is ahead of time. You'll have to pass it through the OpenAI API to actually retrieve the embedding for every sentence. So it's dynamic, it's on the fly, whereas these are already preloaded. This module is just averaging the embedding. So this is simple average. There's no TF-IDF here. We just take every single word and average in the sentence, and then we average the embedding. So I'm looking at a glove embedding of just 50 dimensions. So it's a really small dimensional embedding as compared to OpenAI that we'll also look at. So obviously the results will change. The more dimensions you have, the more information you can encapsulate for a word or a sentence, the better you can do semantic search, right? So we're looking at a 50-dimensional baseline embedding. And so this is you can pass in a sentence here, and then it's going to use the embeddings dictionary, get all the words, get all the embeddings for the words, average them, and then return the sentence embedding. So that's just what this is doing, right? And then we have OpenAI embeddings. So OpenAI embeddings, like we discussed, we set it up here. This is just a wrapper around it, and it also converts the embedding that you get into a NumPy array. So I get a NumPy array coming out of this method. Okay, so we load glove embeddings here, and then we're using some a reference, or let's say these are categories. So like we said, I want to associate every sentence or a paragraph with one of the categories that's kind of closest to the sentence, right? So the gold standard or the reference categories are flower, mountain, tree, car, and building for this demo. What are we doing here? So here we're so here we're getting the OpenAI embeddings for the gold words ahead of time, and I'm storing it in a dictionary here. So for every single gold word or a category, I'm getting an embedding. So that's in NumPy array format. Okay, so that's a dictionary. Okay, this is where the demo is set up. So we set up the title, header, and then we do a similarity search. So this is similarity search. Obviously, I would like to put all of this into a function, but anyway, this is a little bit of a spaghetti code, but we can clean this up later. But anyway, this is just for a demo. So here we're looking at cosine similarity computed through the glove embedding. And here we are looking at cosine similarity computed through the OpenAI embeddings. So I just want to compare for every single query, how does the cosine similarity result for glove differ from OpenAI, right? And then I have set up some other stuff here just to make it look better. Okay, so that's kind of the setup for the embeddings demo. So now this is running on my local host, but you can also host it on Google Cloud or wherever you want to. Streamlit also provides its own, cloud limited functionality cloud, provider where you can also upload your web app. So this is going to be running on my local host. So the way to do it is streamlit run embeddings demo. So this command is going to open up a new window. Let me share that window here. Okay, so this is a web app running on my local host. So search-based retrieval demo. So pass in an input word or even a sentence. And we're looking at 5 categories that are already specified, right? So I'm just going to do a baseline check. So let's say mountains and see what I get. Okay, so based on glove embeddings, the closest word I have between flower, mountain, tree, car, and building is mountain. The cosine similarity is 0.87. And then for OpenAI, small embeddings, so that's the 1500 dimensional embedding. Again, I get mountain. So the baseline is checking out fine, and the cosine similarity is also pretty high. It's higher than 0.5, which gives us confidence. But sometimes it may be less than 0.5, but it's kind of the best result. So that can also happen. But if it's negative, that's something you want to worry about. Okay, so the baseline checks out. Let me try something else, like, I don't know, let's say Tesla, just to check that this is, okay, so both of them refer to a car. And now you see the cosine similarity has gone down. Maybe it's kind of, it shouldn't be so low, but there may be other contexts in which other things can come up. So it might be connected to other words as well. So yeah, This is interesting. So the embeddings are computed based on how the words appear, what other words are connected to the car. So you might actually you might actually go to a mountain with using a car, right? So car is connected to a mountain. So it might actually, there may be reasons why this cosine similarity is low. But anyway, this is the best cosine similarity among all the other words. So that's a good thing, that this is the highest that we are seeing, but it's still a little bit low. Okay. Now let's try some sentences, and you guys can also type in something in the chat that we can try here. Let's say I want to see something like, I love to go for a hike. So what do you think should be the closest category among these five for the sentence?
Mountain, maybe?
Mountain, right? Okay, let's try that. So glove embeddings tells me it's car, but OpenAI tells me it's mountain. Um, car is not a bad option, but it's probably the second option because you have to use a car to drive to a hike. So it makes sense. But the most intuitive thing is mountain. So, um, any other things you want to try? Like something that's a little bit tricky, we can try and see how these embeddings differ. Maybe you can call out a sentence, or you can put it in chat and we can test it here. Anything? Okay, let me see. Someone put something in chat. I want to drive to the forest. Okay, let's try that. Oh, I want to drive to the forest. Okay, this is a tricky one. Okay, so glove embedding for some reason gives me building. um, I'm not sure why, but it's also limited dimensions. There's only 50 dimensions to it. OpenAI says tree. So I think the object of focus is forest. Maybe it's not drive necessarily. So tree actually makes a lot of sense. So with more dimensions, there's better predictability. Um, Anything else you want to try? Okay, let's try something tricky like mountain rose or something, because mountain rose is more of a flower, right? Okay, both of them predicted mountain. Um, yeah, I would think you'd say flower, but any other tricky, or I like taking pictures of wildflowers on a hike. Let's try that. Actually, I should have also output the second best, not just the best. You just take the second highest cosine similarity, and that's the second best word. So someone sort of mentioned this. So I like taking pictures of wildflowers on a hike. Yeah. So would you say flower is closer, right, than a tree or a mountain? Because the object of focus is flower, maybe. So yeah, I think OpenAI does better. And this is the small embedding. So the large embeddings might do even better because it has 3,000 dimensions to compare against. Um, okay, any one last
What
sentence?
about a completely,
Random stuff.
random stuff like I like to go to beach under sun and something like that?
Okay,
Like
I'd like to go to
nothing about
beach.
mountain or hike or car or oh yeah, I like to walk on a beach in a during sunset or something like that.
Yeah, it's a good one. Let's see what it comes up with. Uh, yeah, both of them are incorrect, right? I think there's no right answer. Maybe there's a beach by the mountain, but you can also say there's a building by the beach. But uh, yeah, There's no right answer, but I mean, mountain might make sense if you have beaches that are close to mountain. Um, but yeah, so this is good actually. The cosine similarity being low is actually good because it's not seeing relevance. But for some reason, glove is seeing relevance, so which tells us that it's not a great embedding because it's actually seeing good relevance between building and the sentence. I think it's doing a simple averaging. So the way it did averaging, it might be close to something here. But it's yeah. So you can see that this is actually good that the cosine similarity is low. It's good because we really don't see a high relevance between mountain and this sentence. Um, anything else? Cool. Um, So you'll get to build a demo like this for mini project one, and so you can also not just put it on localhost. You can see here it says localhost 8519. You can also put it on the cloud, and then you can share it around and have people test it as well. It's good. It's good to like try different kinds of embeddings and different ways and see which one performs better. I think there's probably embedding retrieval benchmarks. So one another way to say that this embedding is better than that is over a benchmark, you consistently are able to retrieve the top one or top two, uh, similar categories of words better than any other embedding. So you know your embedding is better. So instead of like just testing it one at a time, you test it across thousands of data points on a benchmark and then say this embedding is better. Um, so I'm sure OpenAI has done its tests over the small and large embeddings, and that's why it's probably very popular to use these embeddings for retrieval in in a company setting or business setting or wherever. Okay. Um, what else? Let me just pause here. So those who are presenting on Wednesday, I think Wednesday is where our first presentation begins, first set of presentations. Each team will have 5 minutes, so 3 minutes to and we don't do live presentations, so your presentation has to be pre-recorded and exactly within 3 minutes because we are really time bound. We're using class time for presentations, so we're really time bound. So 3 minutes of pre-recorded presentation. Make sure both of you, if you have a team, the two of you get to uh, speak through the presentation. And following the 3 minutes, we have 2 minutes of questions. So we'll only have like one or two questions. So two questions, let's say, we'll prep from our side for each paper. So just make sure, as long as you understand the paper, the questions are not going to be very complicated, but it's just going to test your understanding. So definitely encourage that if you're presenting, make sure you understand what's in the paper while you summarize and you can think through the concepts. Then we'll have those 2 minutes. So 5 minutes per team, three presentations, 15 minutes. So the last 15 minutes of Wednesday is going to be presentation. So hopefully this is fun for you guys. We're going to look at, there's so many cutting edge papers that we've listed out. And so feel free to have a blast reading those papers and also other papers and listening to other people present as well. There's so much of information that's going to come in the next through these presentations in addition to lectures. So I think it's going to be a huge learning opportunity. So feel free to go deeper as you feel fit. Okay. Um, Also, one other thing, I think I posted a Calendly, um, you know, calendar slots that you can pick if you want to have a one-on-one. On Tuesday, 4 to 5, I have three slots in the next uh, 6 or 7 weeks until March. Um, Anything that's like a pet project you want to brainstorm or talk about, not related to assignments necessarily, not related to course material, but something that's more something that you're passionate about, we can chat. So feel free to pick a slot there if you're interested. Okay, anything else? Hofe, do you have anything you want to share from your side, grading or?
No.
Okay. Do you want to mention about the in-class exercise, or are we good on that?
About the in-class exercise, uh I'll open the access for the students who is newly joined this class
Okay, cool.
and make sure to finish that quiz.
Yeah, yeah. Okay, sounds good. We'll see you on Wednesday, 4:30. Um, all right, take care.